In this video, I'd like to talk a little bit more about our Unit 1 exam review. In class, we finished around question 7 or 8. I'm going to jump ahead, however, and revisit some of the questions that show up later in this review. We're going to start here around question 16 and work our way towards the end. This will give us an opportunity to review the 2D kinematics equations that we've seen but haven't practiced an awful lot in class. So we're going to start with number 16 here. We have an elevator that's moving upward with a speed of 11 meters per second. So I'm going to call that my initial velocity. 3 seconds later, the elevator is still moving upward, but its speed has been reduced to 5.0 meters per second. So we've got an initial velocity. It looks like a final velocity. We have a change in time of 3 seconds, and they go on later to call it 3.0 seconds. And our job is to find the average acceleration of the elevator. Now, one thing to note is that we are moving upward at 11 meters per second, and our speed has been reduced to 5 meters per second. So it looks like we have velocity in this direction. But since that velocity is slowing, we should see acceleration come out to be a negative number, deceleration in fact. So with this information that's given to us, I kind of feel like the final velocity equation is the one that we're going to work with. We have the two velocities, we have acceleration and time. We're looking for acceleration, that is, and we have our change in time. So I would suggest that we use that function. Final velocity is equal to our initial velocity plus our average acceleration times the change in time. And before we substitute any numbers in, I just wanted to show something real quick on the relationship of this function and the definition of average acceleration. If we were to subtract our initial velocity to the left side of the equation and then divide by delta t, we'd end up with average acceleration is our final velocity minus our initial velocity divided by the change in time. And we might also note that our change in time is really equal to some final time value minus an initial time value. So again, if we look at this as delta v over delta t, that's an appropriate way to see that. And we're basically saying that our object's acceleration is the result in the change in velocity over time. And again, for you calc students, you might recognize this as dv dt, a derivative of the velocity function. And then with our values substituted, our final velocity was 5, initial velocity was 11, divided by the change in time of 3 seconds, that yields a result of negative 2.0 meters per second. Now that's important to note direction here because that negative value does imply that the acceleration is pointing downward, while our velocity was upward, and that does produce a deceleration instance. Now in question 17, we're being asked which of these situations is not possible. A body that has zero velocity and non-zero acceleration. Well, we have seen that before. We've talked about specifically if we're addressing a ball that's being tossed upward once it reaches its peak, there is no vertical velocity. Once the object has kind of reached its high point, there's no vertical velocity, but it's still experiencing vertical acceleration. So I don't think A is a good choice. B, a body traveling with a northward velocity and a northward acceleration. Well, if we have velocity pointing in this direction and acceleration also pointing in that same direction, we're just increasing the velocity of the object, so that's fine. And conversely, if we have a northward velocity but a southward acceleration, well, we're just decelerating that object, so that's definitely possible. A body that travels with constant velocity and a constant but non-zero acceleration, this is one I have a problem with because a non-zero acceleration implies that we have a change in velocity over time, and if we're experiencing a change in velocity, then we can't maintain a constant velocity. So I think D would be the answer here, which is not possible. In number 18, a bullet's fired from a gun and has an initial horizontal and vertical velocity components of 30 meters per second and 40 meters per second respectively. So that means the horizontal component is 30 while the vertical component is 40. We can show that with a simple sketch here, perhaps a free body diagram. So we've got a horizontal velocity of 30 meters per second, a vertical velocity of 40 meters per second. I had to fix that sketch there to make it a little bit more representative. So the question is, what's the initial full speed of the bullet? Well, we have mentioned this once or twice before. The full speed would be the sum of those two vectors. We could say something like this, that the velocity vector, the true velocity of the object, is the sum of its horizontal vector and vertical vector. And rather than focusing on the formal methods for adding these together, let's just remind ourselves that the sum of two vectors would be the result of the tail to tip orientation of the vectors. This one creates a right triangle, so we can use the Pythagorean equation to solve. The velocity of the bullet, or the magnitude of the velocity of the bullet, is going to be the square root of 30 squared plus 40 squared. Now I do need to be a little bit more careful about this. I don't want to be so cavalier as to completely ignore our units here, so let's reintroduce them. We're talking about 30 meters per second squared plus 40 meters per second squared. We can sum those two together because the units are the same, and when we take the square root of our resulting units, meters squared per second squared, that does produce a result of meters per second. Now if you're lucky, you'll notice that this is essentially a 3, 4, 5 triangle, and the math here is going to work out to be 50 meters per second as a result. So if the bullet was fired at this angle, which is currently unknown, the horizontal velocity was 30 meters per second, while the vertical velocity is 40 meters per second. The actual velocity of the bullet along this trajectory is indeed 50 meters per second. So in number 19, we've got an artillery shell that's fired with a horizontal velocity in the positive x direction at the top of an 80-meter high cliff. The shell strikes the ground 1,330 meters from the base of the cliff, and our question is, what's the magnitude of the acceleration of the shell just before it strikes the ground? So we might be thinking, well, the shell is going to impact at an angle, and that would be fine to recognize, and this angled impact is going to be the result of the horizontal vector and vertical vector. So in this case, we're talking about acceleration vectors because the problem is all about acceleration here. It's not velocity vectors, it's just acceleration vectors. So the acceleration in the y direction is equal to negative 9.81 meters per second squared. And the acceleration in the x direction, well, we might think that we've got to compute that. We've got lots of information to work with, but hopefully you recall that this is actually quite easy. The acceleration in the x direction is 0 meters per second. While there's certainly some velocity, this object is moving forward at some rate of speed. As soon as the force that initiated the movement of this object, as soon as that force is removed, there is no longer any horizontal forces experienced, therefore no horizontal acceleration experienced in this situation at all. So while we're looking for the acceleration of this object along the diagonal, technically there is no diagonal here because there is no horizontal here. The only acceleration experienced by this artillery shell is a result of the vertical acceleration due to gravity. And we'll go ahead and report that B is the correct solution here for number 19. Now with number 20, this is actually a question that's similar to some of the questions that were posed in class from students. What happens if a ball is thrown upward, or if we introduce some sort of vertical velocity in the midst of a trajectory problem? Now in this particular case, we're talking about an object that's thrown directly upward, so it goes straight up and then it's going to come straight back down. But the math remains the same. At least our y component math would be exactly the same if we threw this object along an arc as well. So as we read here, we see that our initial velocity ends up being a positive 20 meters per second, so that's a good implication that this object is moving upward. We're letting 4 seconds pass, and we're looking for the final velocity at the end of this event. Now, one thing that we can assume is that we're standing here on Earth when we throw this directly upward, so we have acceleration in the y direction of negative 9.81 meters per second squared. And of course, with this given information, I think our final velocity equation would be the one to work with. Final velocity is the sum of initial velocity plus average acceleration times the change in time. So if we note that final velocity is initial velocity plus acceleration times the change in time, we can sub in our values and compute from there. And a quick check on our units leads me to believe that our setup is perfectly fine. The acceleration unit times the time unit produces meters per second velocity, so that velocity can be added with this velocity, and therefore we will obtain a final velocity measurement as well. And of course I realized a mistake as I was computing this. Our initial velocity was a positive 20 meters per second, so that's going to change some things. If I go to the calculator and take a look at the result here, negative 20, if that was our initial velocity, technically we were throwing the ball downward, it would eventually have gained a velocity of negative 59. If we had thrown the ball upward, then at the end of 4 seconds, it has a velocity of negative 19. So that tells me that we threw the ball upward with 20 meters per second velocity, and after 4 seconds, it's now got a negative velocity, so it must be on its way down. So negative 19.24 meters per second. And if we go back and do a quick check of our significant figures, this has only got 1 sig fig. This one's got 1. This one currently has 3. So we can only retain an answer that's accurate to the least accurate measurement. This negative 19 with 1 significant figure would be negative 20 meters per second. And I think I like C as an answer here. Now with number 21, we have a quarterback that throws a pass at an angle of 35 degrees above the horizontal. So we might sketch that with a velocity vector that looks something like this. So we have 35 degrees above the horizontal. The initial speed is 25 meters per second. And so by the way, we'll note that this is theta. This is our initial velocity. And the ball is caught by a receiver 2.5 seconds later. So this ball was thrown, and it was caught by the receiver that's all the way down here, and the change in time for that event, or through that event, was 2.55 seconds. Our job is to determine the horizontal distance, or range, that the ball was thrown. So how far was it from point of release to point of reception, our delta x. So now if we go to our formula sheet, we have this group of formulas for motion in 2 dimensions. If we're talking about our side view, we sometimes call these free fall, or better yet, projectile motion. I think that would be a better description for these. Projectile motion, because these up here would work for free fall as well. But projectile motion would be another name for these formulas. We have a bunch of given information, or a bunch of formulas that could work. This is the particular one that I'm going to go after here. If we have the initial velocity and the angle at which we're being thrown and the gravitational acceleration here on Earth, we can sub in some values into this form of the equation to calculate delta x, or the range of the football throw. So again, our horizontal range, delta x, is the result of these values here. So we've got an initial velocity of 25 meters per second and an angle measure of 35 degrees and gravitational constant of 9.81. Remember, when we use the value g, we always use the magnitude of acceleration, so the positive equivalent of that. And when I go to the calculator, I see that the result ends up being 59.8682 meters. So 59 point, let's check that again, 8682 meters. Now I started to do this math and I thought of something here. We did not reference our change in time. We didn't reference the piece of information here. And that may or may not be meaningful. In this particular case, though, I think it is, because the answer that we got, which I believe is correct, is not presented as an option over here. And I think one thing that wasn't clear to me at the beginning of this problem was that the flight path of this ball was interrupted by the receiver. So the formula that we were using is good for projectile motion if it was uninterrupted. So if this ball was thrown and not caught by the receiver, but eventually hit the ground, now we're talking about the total distance that this object would have traveled. And I think it becomes clear that, yeah, this ball could have gone 60 meters. However, if it was caught, assume that it was on its way down here and intercepted right about here or caught right about here, then a reasonable answer could be option D. Now, as it turns out, though, we can compute this more directly if we use one of our other formulas from elsewhere in the unit. Now, if you recall, we have this group of equations that we can use too, and I'm going to consider this general position equation for right now. If we're looking for the change in x, then as long as we're provided the initial velocity in the x direction, the acceleration in the x direction, and the amount of time that passes, we can compute the horizontal displacement using the general position equation. So we might say something like this: the change in x is the result of our initial velocity in the x direction times the change in time plus half of our acceleration in the x direction, average acceleration in the x direction, times the change in time squared. And again, this formula could be pertinent even though the ball was tossed in this angular direction. The vertical component of the motion has really no effect on the horizontal component of the direction. If we're ignoring air resistance, there's no outside forces affecting the horizontal distance that this object's going to travel. Now the problem that we have, though, is that the diagonal velocity was given to us at 25 meters per second, but what we really need is the horizontal velocity of this vector. Now here again, if we imagine the diagonal velocity as a resultant, if you will, of a combination of our horizontal and vertical velocities, well, this velocity vector, this horizontal velocity vector, can actually be found using simple trig methods, and we're going to end up using cosine. If we apply cosine of 35 degrees, the resultant ratio would be some velocity horizontal divided by the velocity across the hypotenuse of 25. So that tells me that the horizontal velocity is 25 times cosine of 35. This computation yields our horizontal velocity. We're going to let this velocity continue for 2.55 seconds, plus 1/2 of our horizontal acceleration, which, well, as soon as the object is released by the quarterback, ends up being 0. And again, for our time, the amount of time that passes, 2.55 seconds squared. The seconds squared from this unit and this unit would cancel, and we'd be left with meters as distance. But because there is no acceleration, that results to 0 anyway. And the result of 25 cosine 35 times 2.55 seconds is indeed 52.2209 meters. And this result, 52.2209 meters, I think does confirm that this answer would be a good one. So here again, if the ball was thrown along this trajectory, but was caught before the object had the ability to return back to the ground, and that catch was made at 2.55 seconds during the flight, then evidently the distance that the object has traveled is only 52 meters, whereas the ball had the ability to travel a total of about 59 or 60 meters. I like that problem. It gives us two different scenarios to consider, and the math to complete them is both provided in our formula sheets. So it looks like number 22 is a vector summation problem. We've got a friend that's giving you directions to their house from your current location, and they say to travel this distance in this direction, then travel this distance in that direction, and we're trying to find out if we went in a straight line from beginning to end, how far and in what direction. So what's the magnitude and direction of the resultant vector? So I would approach the problem this way, I think. I would take the 3.3 kilometers and multiply it by cosine of 0 degrees and sine of 0 degrees. To that I would add 1.9 kilometers in the 270 degree direction, and so we're going to compute cosine and sine at 270 degrees, and the result here would give us our x direction and y direction vector. Now we could reach for a calculator and evaluate this expression, but let's not forget our unit circle. Cosine of 0 degrees is 1, and sine of 0 degrees is 0. And cosine of 270 degrees is 0, while sine of 270 degrees is -1. So now these matrices that we've established, they kind of act like grouping symbols, and we could distribute this scalar into both components of the matrix. So 3.3 times 1 is 3.3, plus 1.9 times 0. Well, that's just going to leave us with 3.3. And 3.3 times 0 plus 1.9 times -1 leaves us with -1.9. So now we know that from our starting point to our friend's house is a total of 3.3 units to the right and 1.9 units down. This is where we're going to end up. If we had followed the vectors that they had given us, well, that's quite easy to see now. We're traveling 3.3 east and 1.9 directly south, and we'd end up in the same position. Now, this method here, of course, would be a lot more helpful if our directions were not due east and due south, but any other angle on a compass. To finish answering this question, we just need to do a little bit of trigonometry to obtain this angle measure and this resultant length. So the setup for that trigonometry would look like this. The magnitude of the resultant vector is the square root of the two side lengths squared and summed together, and the angle measure for theta is tangent inverse of our vertical component divided by our horizontal component. And those results end up being 3.8079 and -29.9315 degrees. And the math teacher came out in me here, and I automatically produced a result with 4 decimals, which is okay. But if we consider sig figs, we should really just use 2 significant figures along the way. And 3.8 kilometers at -29, well, -30 degrees would be, I think, the best answer. The answer choices they give us include some decimals, however. So it looks like B or C is the answer. I'm going to go with B here. And this set of directions is a little bit different than the bearings that we've talked about in class. With all of the bearing units that we've given in our class, we would say something like this, 3.8 kilometers, and then we would provide a direction based off of north or south. So I would have said south 60.1 degrees east. So we would face the south direction and turn 60.1 degrees to the east, but their description here is actually generating the same position or same result. If we're saying that we're 29.9 degrees south of east, then I think this description is fair. 29 degrees to the south from an initial direction of east. So I hope that video helps clarify some things. Seeing these example problems hopefully is a benefit while you're preparing for our exam that we will start on Wednesday. As always, send me a message directly. You can send me an email through Butler Tech, or if you can find a way to message me through Blackboard, that would be okay too. I'm just not real sure where the direct message option is there. And I'll try to answer some questions throughout the day tomorrow while I am away. Thanks for watching.